This lesson will cover aspects of mathematical modeling of high-temperature fuel cells. At the end of this lesson, you will be able to describe the differences between non-dimensional models and one-dimensional models and determine for which applications each one can be used. You will be able to sketch qualitative profiles for the main operating variables along the cell length and argue on why they present certain special distributions. And finally, you will be able to discuss the difference between a co-flow, counterflow, and cross-flow geometry and determine which model approach is suitable for each. Among the high-temperature fuel cell that we have introduced, there is molten carbonate fuel cell. The fundamental equation to model fuel cell performance is the Nernst equation. To write the equation for the Nernst potential, we have to look at the electrochemical reactions that take place in the cell. For molten carbonate fuel cell, the overall reaction occurs between hydrogen, oxygen, and carbon dioxide, which is necessary, if you remember, to produce a carbonate ion that can pass through the electrolyte and go from the cathode side to the anode side to transport the oxygen that can then react with the hydrogen to form water. The Nernst potential equation is a function of this ratio between the partial pressure of products and reactants. So the product of the overall reaction are water and the carbon dioxide formed at the anode side. The reactants are the hydrogen, the oxygen, and the carbon dioxide fed at the cathode side. Once we know the Nernst potential, we can use common models for the losses that we have seen in the introductory lesson and calculate voltage and power. Typical values for the temperature in molten carbonate fuel cell is around 600 or 650 degrees centigrade. Current density is usually quite low for this type of fuel cell. 0.2 amps per square centimeter is a common value, which, depending on exact temperature and exact fuel composition, will give a voltage in between 0.75 and 0.9 volt for each cell. So in this way, you can calculate the power density for a cell, and you can see that hundreds or thousands of cells in the stack are needed to reach reasonable amount of power for different applications. Another type of high temperature fuel cell is the solid oxide fuel cell. In this cell, the overall reaction is between hydrogen and oxygen. Oxygen ions are formed on the cathode side and cross the electrolyte to meet the hydrogen and form water. So the Nernst potential can be modeled by taking into account this ratio between the partial pressure of the water and partial pressure of hydrogen and oxygen, which are the reactants. Again, empirical models for the losses can be used to calculate the final fuel cell voltage and power. Typical values of temperature for SOFC are in the range of 800 to 900 degrees C. Current density is usually a bit higher than for molten carbonate fuel cell, going up to 0.5 amps per square centimeter. The voltage is found in a similar range as for MCFC. The level of details of the model depends on the purpose we need to use the model for. Non-dimensional models, also known as black box models, represent a direct relationship between the input and the output. They're based on overall mass and energy balance and calculation of Nernst potential with an average temperature and average pressure. So this type of model is quite simple, and so very useful for analyzing the performance, overall performance of the fuel cell, so for system analysis. One step further in complexity is one-dimensional model. In one-dimensional models, usually the dimension considered is along the direction of the flow, airflow and fuel flow. The fuel cell is divided in segments along direction of the air and the fuel flow. And for each segment, the mass and energy balance is solved, as well as the electrochemical equations. So this type of model is useful to analyze the detailed distribution along the cell of Nernst potential, current, temperature, and all the main variables. One further step in complexity is two-dimensional models, in which also the perpendicular direction to the flow is considered. One difference in one-dimensional model compared to zero-D models is that the heat transfer can be analyzed along the cell. Each segment usually comprises a solid part that represents the solid material of the anode, cathode, the electrolyte, and a gas section that represents the air or the fuel. So we can analyze the heat transfer in each segment, which comprises of the heat conduction between adjacent segments, and is a function of the area between the segments and the temperature of the solid part. Then the heat convection between the solid and the gas, which is a function of the area between solid and gas, the temperature of the solid, and the temperature of the gas. In each segment, we can also analyze the heat generated by the reaction, which is a function of the heat released by the reaction minus the energy used for electrical power. If you analyze the heat transfer along the cell, we will see that the temperature of the solid material is not uniform, but it usually increases following an S shape. This depends on the reaction rate and the cooling effect of the air, because in high temperature fuel cell, the air is not only used to provide the oxygen to the reaction, but also as a cooling agent. At the inlet of the cell, where the air is cooler, the temperature increases more slowly. In the middle part of the cell, the air temperature starts to increase, so the heat transfer to the air is less, and reactions are occurring faster, so the temperature increases faster. At the very end of the cell, reactions are now much slower because there is not much fuel left. The temperature of the air is higher, so but because of the low reaction rate, the solid temperature increase is also slower. This is important to analyze when we want to see when we want to analyze, for example, the thermal stress in the cell, the lifetime of the cell, because the maximum temperature may be much higher than the average temperature. Then we can calculate for zero-D models. Not only the temperature itself, but the temperature gradient is also different than if we consider a uniform or linear increment of temperature along the cell. And this is also important if we want to analyze the lifetime of the cell, because localized high temperature gradients can increase the thermal stress in the ceramic material and can reduce the lifetime of the cell. The nurse potential decreases with increase in temperature and decrease in fuel concentration. So it usually follows almost a linear decrement along the cell. Same thing happened to the common loss terms, activation loss, omic loss. They also decrease almost linearly along the cell. The difference between nurse potential and overall loss is assumed to be almost uniform along the cell. So the voltage can be considered constant. The current density distribution follows the hydrogen distribution, and so it follows very close also nurse potential distribution. So we can see that it also decreases fairly linearly from the inlet of the cell to the outlet if the cell is fed by pure hydrogen. Also in this case, it is important to use a one-dimensional model if we want to analyze the localized value of current, because in the inlet of the cell, the current density may be quite high. So it's also an important information if we want to analyze the lifetime of the cell or things like that. High temperature fuel cells are suitable for fuel containing methane or other hydrocarbons because on-anode reforming is possible. Here we have an example of fuel composition distribution along the cell. In this example, the fuel is a gas mixture containing a certain amount of methane, hydrogen, carbon monoxide, and enough water to avoid carbon deposition. We can see that the methane concentration decreases quickly in the first part of the cell because of the anode reforming. The hydrogen increases a bit in the first part because it's produced by the reforming of the methane, and then it decreases along the cell because reactions are taking place. The water decreases at the inlet because it's consumed during reforming, and then increases since it's a product of the electrochemical reaction. This one-dimensional analysis is important if we want to evaluate, for example, if there is carbon deposition or if there is fuel starvation, so too much hydrogen is consumed, which can cause excessive diffusion loss. But it is also useful to assess the distribution of current, temperature, losses, and other variables when varying the fuel composition. For example, if we have methane in the fuel mixture, the maximum current density would be shifted much more toward the middle of the cell compared to when we have pure hydrogen, because the first part of the cell is used for on-anode reforming, so not many reactions occur to produce current. And more hydrogen is available at the end of the cell because it has been produced by the reformers, so the current density at the end of the cell is higher. So far we have looked at co-flow configuration in which air and fuel flow in the same direction. Another common geometry is the counterflow. In the counterflow configuration, fuel and air flow in opposite directions. And this leads to different profiles for current and temperature distribution. In fact, the temperature, if we look at the direction of the airflow, the temperature follows the same S-shape increment, but the current is specular compared to the co-flow configuration because the maximum value of current density is at the fuel inlet. Another possible configuration is cross-flow. In this geometry, the air and the fuel flow in perpendicular direction. We need a two-dimensional model here to calculate the heat transfer between the solid and gas, because these happen in 2 dimensions. In this case, the reaction proceeds in the direction of the fuel. So the current density decreases in the direction of the fuel and increases in the direction of the airflow due to the different temperature distribution, and so different rate of reaction and different Nernst potential distribution. Another type of modeling is at the microstructural level. This allows to analyze the diffusion of gases and ions in the cell, and also to study the evolution of the materials that constitute the cell over the time. If we zoom in at the size of a molecule, we can define the triple phase boundary. This is the interface between 3 elements: the solid material that is conductive to the oxygen ions, so it's the material that constitutes the electrolyte or the anode, the catalyst, and the pores in the solid material where the fuel can diffuse. So this is where the reaction takes place, because it's where the oxygen ion meet the hydrogen in presence of the catalyst. The anode structure is not rigid. The molecules can move over time, altering the triple phase boundary. Sometimes there are also some degradation mechanisms that take place. For example, the oxygen may react with the catalyst, reducing the triple phase boundary, or impurities may obstruct the fuel passage. This phenomenon can be modeled to assess how the triple phase boundary reduces over time and how this affects performance. No matter at which level you model the fuel cell, one necessary step is always to validate the model with experimental data or with the results from a more complex or more accurate model. It's also important to know what is the range of validity of your model. For example, the way we model Nernst potential is only valid for fuel utilization lower than 90%. If there are other assumptions that you make when writing your mathematical equation, you also have to remember that this may reduce the range of validity of the model. In conclusion, we have seen how 0D models can be used for system analysis. Because they are based on overall mass and energy balance, and the electrochemical equations are a function of the average temperature and average fuel concentration. But if we need to analyze the constraints given, for example, on the maximum current density or the maximum temperature, we need one-dimensional or two-dimensional models. Higher dimensional models capture how the voltage, current, and temperature distribute along the cell and how they depend on each other. But of course, the complexity comes also with a drawback, because these models may be, since they are more complex, may also be slower computational wise. So in those applications where the computational speed is required, for example, for control, for optimization, often 0D models are preferred. In any case, every model needs to be validated against real data or high fidelity models results.